Hello everyone. In the previous session we have studied one of the application of maximum modulus theorem. So we call it as Edmund's three-circle theorem. Now here is the second application of maximum modulus theorem. So it is called as Schwartz lemma. You have to remember along with the statement. So let D is equal to Z such that Z less than 1 and suppose F is analytical in D. Usually they will not ask you to write the statement for this theorem. Anyhow, you have to know that this statement represents Schwartz lemma. Fine. So if f of z is less than or equal to 1 for z in A and f of 0 will be equal to 0, then we have these two conditions is true. That is f dash of 0 is always less than or equal to 1 and f of z is less than or equal to mod z for all z in disk D. Similarly, f dash of 0 will be equal to 1 if f of z is equal to 1. Meaning is this condition is true only when f of z is equal to z. So for some z not equal to 0, then there is a constant c such that mod c is equal to 1 such that f of z is equal to cz for all z in D. Fine. So this represents a Schwartz lemma. Now I am going to define a function g. For the proof, let me define a function g which is on a domain D such that g will be from D to C. C is a complex plane. Fine. Let me define a function as g of z as f of z by z, and z should not be equal to 0. Why? Because if z is equal to 0, it goes to infinity, then g of z will not be analytical. But g should be analytical, right? So g is analytical. In order to become this function to be analytic, z should not be equal to 0. And moreover, g of 0 will be equal to f dash of 0. Fine. See, g of 0 will be equal to f dash of 0. Now let me prove I have just defined the function in domain D. This will be a function in a domain D. Now let me prove the first statement. So I can write for the first statement. To prove the first statement, see here the meaning of the statement is the complex plane satisfies these two conditions. It is obvious. Fine. So we need to prove these two are also true. If this is true, we need to prove this is also true. Fine. So first one we have to prove that f dash of 0 is less than or equal to 1 and f of z will be less than or equal to mod z. Right. So it is enough to prove that mod of f dash of z will be less than or equal to mod z. So if this is true, this condition is obvious. Fine. So to prove that, let us consider a z value which is less than r, and moreover this r value will be in between 0 and 1. Why? Because f of z is defined between 1 and 0. So I have taken r as in between 0 and 1. Now let me take g of z. Function I am going to consider. So I can write g of z as f of z divided by z. Why? Because I have defined function g of z. So as I already told you, when you are going to split the modulus, so you will get less than or equal to modulus of f of z divided by modulus of z. Again, which will be less than or equal to. Now look at the first condition. What is the first condition they have given? They have given that, see here, I'll just write for your reference, from condition A, mod of f of z is less than or equal to 1, right? So I can write this value is less than or equal to 1 divided by mod z. This is because from condition A, f of z is less than 1. Therefore, I can write mod of g of z will be less than or equal to 1 by mod z. But mod z we have assumed it as r, right? So g of z should be less than or equal to 1 by r. Meaning is that this function g attains its maximum at its boundary. Fine. Now let me take a limit as r tending to 1. Therefore, taking limit as r tending to 1, we get mod of g of z will be less than or equal to 1 for all z belongs to D. This implies that, see here, 1 is none other than, f of z is less than or equal to 1 and g of z is less than or equal to 1. So from a condition and this condition, I'll just repeat once again, from this condition and the condition given in the theorem statement is mod of f of z is less than or equal to 1, right? So from these two conditions, I can write that mod of f of z will be less than or equal to mod z for all z belongs to D. Fine. Also, it is true for its derivative, that is f dash of 0 will be equal to g of 0, which is again less than or equal to 1. Fine. Why? Because we have already assumed that what is the value of f dash of 0? F dash of 0 is g of 0. That is what I have written. When you are going to take modulus, since f of z is less than or equal to z, so f dash of 0 will be less than or equal to 1. Fine. So this condition we need to prove. if this is true, as I already told, if this is true, this is obvious, so that is why I have written here. So in order to prove this statement, it is enough to prove mod of f of z is less than mod z. What I have done is I have defined a function in such a manner that g of z is f of z divided by z. Since I have considered magnitude of g of z, I can split this by using the concept of modulus of a function. So g of z will be less than or equal to mod z. Mod z is r. Since this function attains maximum at r, by maximum modulus theorem, I will take limit as z r tending to 1, you will get this value. So here f of z is less than or equal to 1, so g of z is also satisfying the same condition. Meaning is that both the functions attain the maximum of 1 at the boundary. So these two functions will be acting same. So mod z is less than or equal to r. Therefore, at which value they are acting it as same, that is mod z less than r, right? So therefore f of z will be less than or equal to mod z. So if this is true, as I already told you, this is also true. Hence the proof of first one. Now let me prove the second one. Fine. Now coming to the proof of second one. So second one is also same. As I already told you, if we prove f of z is equal to mod z, it is obvious that f dash of 0 will be equal to 1 by the maximum modulus theorem. So let me prove the second one here. So to prove the second one, let me take that suppose magnitude of f of z is equal to mod z. Meaning is what we have defined the function as, see here, we have defined the function as g of z is equal to f of z by z. What I am going to do is, I am going to take mod of f of z as z for all z in D. If that was the case, what is the value of mod g of z will become? It is mod f of z by mod z, right? So what I have taken, it is just for your understanding. Anyhow, it will be not, it is, all these steps are not mentioned in the notes, so I am just explaining for your reference. Now I am going to replace mod f of z with mod z, so you will get mod z by mod z, so it will get cancelled. F of z replaced when you are going to replace f of z by mod z, so you will get mod of g of z will be equal to 1, right? So I'll just write here mod of g of z will be equal to 1 for all z belongs to D. And moreover, this g will be analytical, right? So what is the maximum modulus theorem says? If g is an analytical in a region D, then g should have a constant function, right? By maximum modulus theorem, statement of maximum modulus theorem, we go through that. So by maximum modulus theorem, g should attain some constant, that is g of z should attain some constant value, say c. So if this is true, we can write by taking modulus on both sides, we can write that this expression is also true. Fine. So if this was the case, since it is a constant, we can say it as, since g of z is equal to 1, since g of z is also equal to c, by these two conditions I can write magnitude of g of z, or else I just replace magnitude of g of z with 1, so that you will get magnitude of c is equal to 1, right? Since what I have assumed the function is magnitude of f of z is mod z, so what it implies is f of z is equal to z, right? By removing the magnitude, so I can write the same as f of z is equal to c into z. Why? Because c value is 1, so 1 into z is same, so I can write this as c into z. Fine. Meaning is that suppose whenever we have f dash of 0 is 1, see here what I have assumed function f dash of 0 is equal to g of 0, that is what the function is defined. So if f dash of 0 is 1, we can say that g of 0 is also equal to 1. Meaning is the function g attains its maximum at 0. So this is what we require to prove is, see here, mod of f of z is equal to z. So if we take mod of f of z is equal to z, what we have proved is f dash of 0 is equal to 1. F dash of 0 is equal to 1. So I have assumed that this condition is true, and I have obtained that f dash of 0 is equal to 1. So hence the proof of Schwartz lemma. So here is the next theorem. It is called as Weierstrass theorem. Anyhow, in some of the year, I don't remember the year exactly, in that year they have given this statement instead of asking state and prove Weistras theorem. Remember, Weierstrass factorization theorem is there in 4th lesson, so it is Weierstrass theorem. You just remember, it is Weierstrass theorem is different from Weierstrass factorization theorem. Anyhow, you will come to study that in 4th unit. So this is only Weierstrass theorem. It says that if z is equal to a is an isolated essential singularity of an analytical function f of z, and k is disk z minus a such that 0 to r be a neighborhood of the point a here. Fine. Then given any epsilon greater than 0 and any complex number xi, there exists a point z such that it satisfies this condition. Fine. Now coming to the proof part, first let me write the given data. So what is given? Suppose epsilon greater than 0 is given and let xi be any complex number, then what it satisfies? This satisfies the condition f of z minus xi will be less than epsilon in the region 0 less than mod z minus a less than r. So this is what the given data. Now I can write the same as, see, just I'll take the reciprocal of this. When you're going to take reciprocal, inequality get reverses. Suppose when you have less than, if your reciprocal of less than is greater than, reciprocal of less than or equal to is greater than equal to. So I'll just take reciprocal so that you will get 1 divided by f of z minus xi is greater than 1 by epsilon. I'm sorry, it is it is less than, right? Oh, I'm sorry. In the given problem, it is given that it is less than epsilon. Let us take that contradiction. I'll just prove it by contradiction method. Fine. Suppose that if this value is greater than epsilon. In the given problem, it is given that less than epsilon. But what I'm going to assume is, suppose if it is greater than epsilon, then when you're going to take reciprocal, it will be less than 1 by epsilon. So let me take this value as m. I'll just repeat once again. In the problem, it is given less than. Suppose that if this condition is not satisfying, in the sense if it is greater than epsilon, what will happen? So I'll just take reciprocal and we'll take this as m. Fine. Now this will be having singularity at a point a. Given as this function is having singularity at a point a. Now I have done a Riemann theorem. So as per the Riemann theorem, this removable singularity, this function has removable singularity at z is equal to a. Once this singularity is removed, then this function will be having an expansion. As per the Riemann theorem, I can write 1 by f of z minus xi can be written as c0 plus c1 into z minus a plus c2 into z minus a whole square plus so on. So this will be the expansion as per the Riemann theorem. Right? Now there will be two cases. If c0 is not equal to 0, what happens if this first term, that is c0, is not equal to 0? Let me do here. Then we can define this function f of a. Why? Because a is the singularity. Fine. Z is equal to a is the singularity of this function. So I'll just replace z with a. So we can define this function as equal to c0 at z is equal to a. Why? Because c0 will not be equal to 0. So we can define this function at the point c0 at z is equal to a. Fine. So I'll just take reciprocal again so that you will get f of a minus xi will be equal to 1 by c0. Again, let me simplify. I'll just shift this term. So you will get 1 by c0 plus xi. Fine. If suppose that this function f of a is defined, if f of a is defined, then defined as 1 by c0 plus xi, then 1 divided by f of z minus xi becomes analytical at z is equal to a. Meaning is that if this is defined as in terms of a complex number xi, then f of a is also then f1 divided by f of z minus xi is also defined. So meaning of defined is it is analytical at z is equal to a. So if 1 divided by f of z minus xi is analytical, I can write f of z minus xi is also analytical at the same point, analytical at z is equal to a. So if f of z minus xi is analytical, we can write f of z is also analytical. Something like if a is real number, if a is if a is even number, then if you multiply one more even number, you will get a even number only. Something like if a by b is analytical, then we can say b is also analytical. So if b minus a is analytical, we can say a is also analytical, something like that. So if 1 by f of z minus xi is analytical, I can say denominator is analytical. So if something is subtracted, this is analytical. So I can say this is also analytical. So f of z is analytical. at z is equal to a. Fine, but look at the given theorem statement. Let z is equal to a is an isolated essential singularity of analytical function f of z, and k is given that inside this region of neighborhood of a, then given epsilon greater than 0 and any complex number, there exists a point such that it satisfies this condition. What we have assumed is, it is not true, that is contradiction. See here, z is equal to a is an isolated essential singularity, in the sense at the point z is equal to a, the function f of z will not become analytical. Meaning of isolated singularity is, if you substitute z is equal to a in a function f of z, then it will not become an isolated singular, it is not become an analytical function. I'll give you simple example. See here, if f of z is equal to 1 divided by z minus a, so this function will not be analytical at z is equal to a, right? Then why? Because if you substitute z is equal to a, this will become infinity, so this function will not become an analytical. So z is equal to a is an isolated singularity, therefore f of z will not be an analytical at that particular point, right? So this will be an analytical only when it satisfies this condition. But what we have assumed is contradiction, that is, it is greater than epsilon. Even though if we assume this condition, what we arrived is f of z is analytical at z is equal to a. See here, as per the statement, this will be true. F of z will become an analytical function only when this condition is true. But what I have assumed is contrary, that is greater than epsilon I have assumed. But what I have proved is f of z is analytical, right? So this will not happen. So this is a contradiction. Fine. Therefore, z is equal to a should be an essential singularity. I'll just continue. So, therefore, z is equal to a is essential singularity. So, that should be a singular point. Fine. Case 2. Case 2 is, suppose if all the constants, whatever the constant we have in this expression 1, C0, C1, C2, C3, everything up to Cm minus 1, everything will be equal to 0, but Cm is not equal to 0, one particular value, last value is not equal to 0. Then equation 1 can be written as 1 divided by f of z minus z will be equal to, see here, up to c, somewhere here you will be having Cm minus 1, again in terms of Cm, so up to Cm minus 1 it will be 0. So what you left with is Cm into z minus a power of m. See here, whenever you have 1 here, you have power 1, 2 here, so you have power 2. So I can write this as plus Cm plus 1 into z minus a power of m plus 1 plus so on. Now let me take z minus a power of m as a common term. So you will get Cm plus Cm plus 1 into z minus a plus so on, right? Now you can clearly observe that z is equal to a is a pole. Z is equal to a. Why? Because when you substitute a in this particular expression, you will get a pole. So z is equal to a is a pole which is of order m. Pole of order m for a function 1 divided by f of z minus z. Hence we can write f of z minus z has a pole. So if this is a pole of this function, I can write this is pole for this function as well. F of z minus z has a pole of order m at z is equal to a, but which is a contradiction, right? Why? Because z is equal to a is an essential singularity, it cannot be a pole. As per the given statement, if we assume that if this expression is true, that is 1 by f of z minus I is less than 1 by, this one, f of z minus I is greater than epsilon, then z is equal to a should be an essential singularity, isolated essential singularity. But what we have arrived is it is a pole, so it is contradiction to our assumption. Therefore z should be an essential singularity. So if it has to satisfy only when mod of f of z minus z should be less than epsilon. Fine. So in both the cases we have arrived the contradiction. Therefore what we assumed is wrong, that is f of z minus z should be less than epsilon. So we have proved this by contradiction method. So this theorem is important. It is asked in one of the year. Please go through this video and practice the theorem. Anyhow, notes of the same will be forwarded in the group. So continue in the next session. Thank you.